A very good day to both my panels, Mr. Kiai and Dr. Sharin. My name is Ivan and I will be presenting to you on my FYP entitled Performance of Thin Copper Wire and Bare Copper Wire for Solar PV Cables. In general, this will be the arrangement on how this presentation will be delivered. So, for the introduction here, we have a snapshot from a newspaper article encouraging the installation of solar panels on households. This is because solar energy is one of the most promising sources of clean energy for Malaysia, as Malaysia are strategically located near the equator and within the tropical climate zone. So here is a design of a thin copper solar PV cable along with its specification. As we all know, solar PV cable is actually one of the key components in PV system. However, the R&D, research and development of solar PV cables are still relatively neglected. So the solar PV cables that we can find in the market today are manufactured under the marine cable standard, hence the thin copper conductor. However, when thin copper conductor is used as a conductor, it raises the issue of eco-friendliness. This is because thin copper are not recyclable. On top of that, there are no concrete evidence to indicate that thin copper can perform better than bare copper under humid and high temperature environment. Next, there are also no evidence to conclude that the rate of electrochemical corrosion in bare copper solar PV cable are higher than thin copper solar PV cable. Lastly is that the price of thin copper conductor is more expensive than bare copper conductor due to electroplating. Here are the objectives of this project. The first is to carry out the test for thin copper and bare copper cables in accordance to the respective standard. Second is to analyze the performance between thin copper and bare copper cables. And thirdly is to examine and justify the effect of electrochemical corrosion on the respective cable samples. The topics covered by this report extend to the comparison of cable samples with thin copper and bare copper conductor, and the test conducted is accordance to EN 50618 and IEC 62930. As for the literature review, I will be comparing these four standards for PV cables. The first comparison will be on the structure of PV cables. According to this table, the rated voltage for solar cable is 1800 VDC for the 2PFG standard, while the other three standards have a rated voltage of 1500 VDC for their cables. Additionally, the manufacturing of Class 5 thin copper cables are regulated in all the standards, whereas the manufacturing of Class 2 thin copper conductors can only be found in the IEC standard. Furthermore, the specification on the quantity of thin is only being mentioned in EN and IEC standard, and the range of conductor size for solar PV cables is as tabulated. The next comparison will be on the electrical properties of PV cables. Accordingly, the conductor resistance should be compliant to 6 or 228 standard from British Standard BS or International Electrotechnical Commission IEC. Next, the voltage test on the completed PV cables shall be in accordance to Clause 6 of the EN 50395 standard, whereby the samples can either be tested under 6.5 kV of AC voltage for 5 minutes or 1.5 kV of DC voltage for 5 minutes. As for the comparison of PV cables in terms of environmental properties, it is noticeable that under the damp heat test, the changes in tensile strength for the insulation ensured, as well as the changes in the elongation of break for both the insulation ensured, should be under 30% for all the standards. Though the focus of EN, IEC and NBT standards will be on the shape of the cable samples. On the other hand, the weather or UV test is carried out on cable samples to simulate the sunny and rainy environment. Next, for the research methodology, the initially proposed cable samples consist of 6 mm² bare copper solar cable, 6 mm² thin copper solar cable, 16 mm² bare copper solar cable, and 16 mm² thin copper solar cable. However, due to the outbreak of the COVID-19 pandemic, MasterTech, the company that I am attached with, is forced to cease operation, and this resulted in the inability to procure the necessary solar cables in time. Nonetheless, to carry on with this experiment, only 6 mm² thin copper solar cable and 16 mm² bare copper PVC cable are used, as only these two samples are available. Due to the limitation and differences in cable samples, a few assumptions had been made and will be discussed at the end of research methodology. Generally, the research methodology consists of 3 experiments as follows. The first experiment that will be discussed is the conductivity test, whereby it is performed to measure the DC resistance of the cable's conductor, and the setup of the experiment is as shown in the picture. Next, I will be showing a clip on how this experiment is performed from BASEC. Next, for the loading test of the solar cable, 3 cable samples of length 20 meter is first prepared and immersed in the water bath of 20 degrees Celsius as shown in the picture. Then an AC voltage of magnitude 6.5 kV is applied to the cable samples for 5 minutes via high voltage tester. Subsequently, the cable is examined whether breakdown happens. As for the loading test for the PVC insulated cable, the procedure for this experiment is the same as the loading test for solar cable. The only difference is that only AC voltage of magnitude 2.5 kV is applied to the cable samples instead of the 6.5 kV. Now for the damp heat test, 3 samples of each cable with length 2 meter is prepared and placed in a testing chamber. A container of water is also added into the testing chamber to simulate high humidity environment. Then the temperature is gradually increased to 90 degrees Celsius and the samples are heated for 1000 hours. Later, at the end of the experiment, the temperature is gradually decreased to 25 degrees Celsius. And here is a picture of cable samples in the thermal oven for this experiment. In regard for the dry heat test, the procedure are the same as damp heat test, except that humidity of thermal oven is being kept as low as possible, and therefore there is no need to add a container of water in the thermal oven. Other than that, the cable samples are only heated to 70 degrees Celsius for a period of 16 hours. Altogether, here are the flows on how the sets of experiments will be conducted. The main limitation for this research is the different cable samples used. Therefore, to make up for the constraint, the equation of percentage of change of resistivity is being proposed as shown. This is because the change of resistivity of metal conductor happens due to oxidation. Therefore, when the percentage of change of resistivity is determined, we can deduce and compare the rate of oxidation with respect to the cable samples. On the other hand, the equation for the percentage of change of resistivity is only dependent on the resistance. Assuming that the cross-sectional area and the length of cable remain constant throughout the experiment. Now for the results of loading test. The table here shows the measured conductor resistance with respect to the cable samples before loading test. The formulas shown here are used to standardize the parameters of cable samples to a length of 1 km and a temperature of 20 degrees Celsius, whereas the tabulated data shows the standardized conductor resistance of respective cable samples before loading test. So after the loading test, no breakdowns of cable samples is observed. The high voltage tester shown here is used to determine whether breakdown happens in cable samples. The table here presents the standardized conductor resistance of respective cable samples after loading test, whereas the table here tabulated the standardized conductor resistance value of respective cable samples before thermal test. Next, this table shows the standardized value of conductor resistance for the respective cable samples after the thermal test. Lastly, this table tabulates the percentage of change of resistivity for the cable samples with respect to the experiment conducted. All in all, the loading test shows that bare copper cable can resist oxidation better than thin copper at high potential, whereas there are no significant changes to the cable samples when subjected under the thermal test. As for the future work, the test can be conducted using the initially proposed cable samples to improve the reliability of the data collected. Furthermore, the cable samples should also be subjected to X-ray fluorescence spectroscopy or optical emission spectroscopy to determine changes in chemical composition and the rate of oxidation before and after the respective tests. And that is all from me. Should you have any questions or inquiry, I can be reached at this email and my contact number. And thank you.